are discussing one-dimensional diffusion equation, and in last lecture we have seen how we can perform an analytical solution in one-dimensional diffusion equation. We have seen that the solution can be expressed as an infinite series. Each term of this series has a function of time and a function of space. Now in this lecture we will try the first technique of numerical solution of one-dimensional transient diffusion, and this technique is the explicit technique or explicit scheme of discretization. That is how we will name this scheme. Also we will see a computer program. We will not write it here, I have already written it. I'll show it to you and show the essential features of the computer program, and that program result that is coming from that program we'll try to verify with the analytical solution that we have performed in previous lecture. So let's proceed then. Here we have taken our governing equation as del t equals alpha del 2t del x2. I am keeping this dimensional form. Now the first step of solving this equation is to discretize the domain. In this case we are using uniform grid of size delta x and uniform time step of delta t. So what is our domain? Our domain is x equals 0 to x equals L, and in this domain I have uniformly divided this domain using this blue dots. Each of this blue dot is a point where we'll get the solution of t. In between these blue dots we don't know anything. So the domain, which was a continuous line between x equal to 0 to x equal to L, we have now discretized. That means we are only seeking solution in certain discrete points, which in this case are delta x apart from each other. Now here these points, I give this an index of I, and the first point is I equals 1 and the last point is I equals m. Now as the time progresses, I want to show the result of what happens at these discrete points. Therefore I have also put this discrete point in delta t apart in vertical direction here, that is the time direction. So at any point you see here, it has a space dimension and a time dimension. In time dimension my index is n. N starts from here and it goes above. So for any point, let us say this point, it has certain x index, that is I, and it has certain time index, that is n. The point left side of it, that has a space index of I minus 1, but this is still at time n because this horizontal line indicates nth time. Similarly, the another green point, which is the right side of my point of interest, index of that point will be I plus 1 n, that is I plus 1 in space, n in time. The point right above this blue point is my rate point. For the rate point and the blue point, the space index is same, so they are both at I, but the rate point above this blue, the index of that will be I in space, n plus 1 in time. Similarly, rate point below this blue, that would be I in space, n minus 1 in time. This is the way we visualize our grid system, and now the domain is discretized, which means that in the domain we are only interested about discrete points where we will get the solution. That way we have discretized the domain, but now we have to discretize the governing equation here. To discretize the governing equation, what we do is something we call forward in time and central in space type scheme. That means we will march in time, that is quite obvious. So we are marching from time level n to time level n plus 1 at a spatial location I. So see, every t has two indexes here. One is the subscript, that is I, that gives us the spatial location, and the superscript, that is n, that gives us the temporal location. So when I say ti n plus 1, what I mean is that this is my ti and this is n plus 1. That means this red point here at the top, that is my ti n plus 1, and ti n is just below that, this blue point. So delta t is time interval between this, which means this time derivative del t, we are representing it as ti n plus 1 minus ti n divided by delta t. If you perform a Taylor series analysis here, you will see that a truncation error will be of the order of delta t. But right now, let's first discretize the equation. This is the first term we have discretized, but we have another term. The second term is the derivative in space. So here we know how to do this differentiation numerically. So I have ti minus 1 minus 2 ti plus ti plus 1 divided by delta x square. So the question is that what should be the superscript here? So at what time level I'll calculate this? Here in time derivative, that question doesn't arise because I am taking this difference between n plus 1 to n at ith point in space. Here I want to calculate the double derivative at ith point in space, but I'll calculate it as nth time level or n plus 1th time level. Both are present in this time derivative. In analytical solutions, such questions will never appear, but here we have to answer this question. So there are actually many answers of this question, and we will see this, but right now this explicit scheme, it will give us one answer and we will go with that. What explicit scheme does is as follows. This question, it answers in a simple way. It says that, all right, I'll take this at nth time step. So now I have the time derivative discretized. This is the spatial derivative discretized. I can bring everything together in my governing equation, and in the governing equation, when I put this, I have, this is my time derivative, this is my spatial derivative, and if you do a Taylor series analysis, which I am avoiding here, you all know how to do it, so you can do it by yourself. In this Taylor series analysis, you will get this truncation error, that is first order in time, second order in space, del t del x square, truncation error. Now what you see is that here only one n plus 1th time level, everything else is at nth time level. So I can take all this nth time level at right hand side and n plus 1th time level on left hand side. These are my current value and this is my new value, that is my unknown. Right hand side is completely known. If you look at the grid picture here, and this kind of picture is called stencil. In this stencil, I am calculating the rate point, that is ti n plus 1. This is n plus 1th time step, and this is I, spatial location, and ti n plus 1 is given by tin I minus 1n and I plus 1n, means these 3 points. So when I am going for n plus 1th time step, I already know all the nth time step values. Therefore, this equation, which is my difference equation, so my differential equation is now converted to a difference equation, and in this difference equation you see that I have only one unknown ti n plus 1, everything else is known. Therefore I can simply calculate it from here. I'll start from n equal to 0, means my initial condition, and then I'll calculate n equal 1, n equals 2, etc., etc., one time level at a time, and I can keep on doing this. So it's a very simple technique and we have to see its efficacy. But now let us just write properly that how we'll solve using explicit scheme. Once again, this is my explicit scheme and this is the stencil. The greatest idea of explicit scheme, and it's a very popular scheme. The reason for its popularity is its simplicity, that it doesn't require much of an effort. It's only simple calculation here. So how we are going to solve it? So we start from an initial condition. This is known to us. Because this is known to us, ti 0, this is the 0th time level, means initial condition that is known to us. Then I'll take the first time step and I'll calculate for n equals 1. This is tin plus 1, so tin, etc., etc. So this is how I'll go on for n equals 2, n equals 3, etc. I'll apply the boundary condition after every time step. The algorithm continues up to desired time level. So this is where n goes to 1, not really n equals 1, because n equals 0 here. So n goes from 0 to 1 here. Okay. So as I said, the scheme is popular because it doesn't require the solution of equations. Its limitations, of course, is there, and we'll discuss it in due course. So this is a Python program that I have specifically created for solving diffusion equation, one-dimensional, explicit. The program has 2 parts. The first part, that is here, it is calculating the explicit diffusion equation, and in the second part, this is the analytical solution. And then here I am plotting both the analytical as well as the explicit solution. So let's see the structure. So what I am doing here, this nx here is my discretization in x direction. 101 points I am taking, so 100 number of delta x's here. The total domain size is 1. I have kept it as non-dimensional, so domain size is 1 divided by nx minus 1, that is 100. That gives my delta x, that is dx. Time wise, I am taking this 10,001 time level. That means this dt, that is my delta t, is 10 raised to minus 5. As I go from 0 to 1, I take a dt of 10 raised to minus 5. Then I go from 1 to 2, I take 10 raised to minus 5, so on and so forth. Limit of sum, pi square, etc. They are only important in this analytical solution, and I'll talk about it later. Now I create this x grid with this x linspace command, and this is giving us the points on the x-axis where I'll find my temperature. Similarly, this time t small t is time, that is I am initializing as an array of size this nt. U is my unknown here, which is temperature, and that is an array, numpy array, which is of the size of nt nx. So all the data I am storing, this is not a very good programming practice, but this is for the sake of just checking it up here. I am storing all the data, all time level and in all spatial points. So this complete nt nx, the complete array is being stored, and then there is uex, that is the exact solution. That is again another array of same size. Now here this u 0 colon, that means at initial time u is equal to 1. That is my initial condition. T, of course, initial time is 0, and r, that is delta x by delta x square, that is coming in our calculation. So now I have this for loop. In this for loop, first I update this t. This t is not really necessary for u calculation here, but it will be necessary for calculating u analytically. For numerical calculation, actually this one line is sufficient. This line says that for all I, that is 1 to nx minus 1, I have this u n plus 1i is equal to whatever the difference equation I was getting there, u ni plus r of I minus 1, I and I plus 1. That is the double derivative part. Now you may be wondering, where is the boundary condition I am using? So boundary conditions are 0. So that is at I equals 0, it is 0. And I equals nx minus 1, it is 0. This for loop will run from 1 to nx minus 2. So 0, it is 0, and nx minus 1, it is 0. That because I have initialized u with 0, they are 0 all the time. So that is why I didn't write it. But this is of course not a very good programming practice. It's better to specifically write the boundary condition. So that is why I have noted it here, that boundary conditions are u equals 0, which are already set by the initialization of u, that is np dot zeros. I am not disturbing those points, n points, n equals 0, n equals minus 1. I am not disturbing them. So they will remain 0. That way boundary condition is already enforced. So this u calculation, what is happening here, this completes our explicit calculation of temperature. You can see that how simple it is. In one line pretty much it is complete. Now for the calculation of the analytical solution, the analytical solution we have already established in previous lectures. It has two terms. One is this time dependent term, that is this pi square is, you can see this pi multiplied by pi, this n square pi square t minus. So you remember that is coming within time dependent term. And in x dependent term I have sine n and pi and x. And then I am taking their outer product. So these are two vectors, ut and ux. So this is ut, ux transpose. And then this is an infinite series. So I am summing up over number of terms that I have to decide how many. I have taken here 1000 terms, but that is actually slightly unnecessary. Even if you take 10-20 terms, you will see a good match. Here hopefully we will see an excellent match, and then you know that in analytical solution 4 by pi will come. So I am multiplying with 4 by pi this uex. So here I complete the calculation. Then I plot the solution. Here this uex I am plotting, and u I am plotting. Uex are exact solution, and u are the solution that are coming from this explicit case. So now we can run the case and see what happens. To run the case, this is actually a spider environment. This is not Jupyter Lab. This is a slightly different environment, but this is as good as others. So if I run it from here, it runs here, and the plot should appear here. So you can see the plot here. Here, this U, EX, they are line. So all three lines are exact solution, and these dots are U, U, U at different time levels. So they are, these red dots are our numerical solution. So clearly you can see that they are falling one over another, and that gives us a confidence that the calculation that we are doing probably are all right. And it also shows that how easy it is to calculate in explicitly. Of course, explicit scheme has its own problem, and we will talk about it later, but you can see that very easily you can calculate the one-dimensional unsteady diffusion equation. It is actually a much easier process than the analytical solution, which is a more tedious process. But analytical solution, the great thing about it is that its accuracy is unquestionable if you take sufficiently large number of terms from the infinite series. So again, we are here. This is the plot that we have just developed, and I brought the plot here. What I have conducted, that is an explicit solution for dimensionless case, and the corresponding analytical solution which we have derived before is this. And here the explicit solutions are red dot, analytical solutions are line, and clearly they are falling one over another. This is the way to verify numerical solution, you are doing right thing or not. And clearly the physical pattern, what we expect, that the temperature starts from 1 and then it goes toward 0, that is also there. So now we have seen the explicit solution technique for transient diffusion equation. And for your exercise, you can write this program what I have shown you and play around with it. If you cannot, then write a pseudocode for solving one-dimensional unsteady diffusion equation using explicit scheme. Thank you. That's all for this lecture. I'll see you in next class.